You wanted, right?
Yes.
Perfect.
Yeah, I think Robert.
Not good.
Early now.
Hello, good morning. We still have two homeworks remaining. One is optional. Notice that homework 11 is optional, but the content of homework 11 is not optional. In fact, there will surely be questions from that. There's about 50 to 60% of the questions will be before midterm pre, and remaining will be after midterm pre. I want to make one comment regarding aiming for higher grades. I think I might not have conveyed it clearly. Let me rephrase that in slightly different words. One of the guidelines I use while curving at the end of the exam is that your grade doesn't change on a global scale for the whole school. I try my best not to change, but if you do very bad in the exam, the grades will change. The same thing if you do very good in the exam, your grades can change, but that's unusual. It doesn't happen too much. So if your grades are not close to your borderline, be careful with how much time you're putting in at this point of the point in the semester. So that's a comment I wanted to make. Again, the guideline I use for the whole class is that your grades do not change at this stage. So be careful with what you attempt. Any comments or questions like that? We started working on ray optics. Broadly, the subject is called optics, but we noticed that the electromagnetic wave, the way it is called, it is a wave, but often it is very convenient and a lot simpler in analysis when you approximate that wave into a ray. So, what's the difference between ray optics and wave optics? Electromagnetic wave, or for that matter, most of the wave have an oscillation in some physical quantity. Like if you're thinking of an ocean wave, it is actually the surface height of the surface that has these perturbations. But here, an electromagnetic wave, it is the electric and magnetic field at a certain point in space that is oscillating. In fact, electric field, the oscillations in electric field can create oscillations in magnetic field, and oscillations in magnetic field can create oscillations in electric field in such a way that they can sustain each other, and you do not need a charge or a moving charge for creating electric or magnetic field. So that's the non-trivial part of it. So that's your electric field, and that's your magnetic field, and they're perpendicular to each other. And this is the direction of propagation. Often use the letter K for this. So this is direction of propagation. Often you need to take care of all these three properties, that is electric field, magnetic field, the amplitude of the electric field, all of that play an important role, and that's wave optics. So that's a lot more effort has to be put into the analysis of such a configuration. But if the wavelength, which is the distance between spatial distance between two maxima, or for that matter any two periodic points, that's called the wavelength. And if the wavelength is large, in fact very large, double greater than sign means it is very large compared to the irregularities on an interface. So irregularities is on an interface. In that particular approximation, it is possible to have a significant simplification of not worrying about all these details, that there is an electric field oscillating, there is a magnetic field oscillating, they are in different direction, they are periodic with this with the spatial periodicity in that. And the only thing that plays an important role is the direction of propagation, and this whole wave is approximated as a ray. So that's the ray. Basically, it's an oriented line, a straight line, but its direction comes into our picture, and that's your direction of propagation. And as you can see, that simplification cannot be even visually enough. That's one straight line versus all the details. It makes the analysis of a problem significantly. So we use the idea of law of reflection. At this, historically speaking, optics was a completely independent field in relation to electricity and magnetism. So all the laws were independently developed there. But at this stage, when you look back, all those laws can be derived using electricity and magnetism. So they don't have to be called a law. In fact, that will just come out to be one homework problem, in a sense that you can use the Gaussian law and Ampere's law to derive the law of reflection. But while we are studying ray optics, let's keep that as a law itself. And what it states is that at any interface, so you have an interface which basically means that this is metal, right? A metal does not allow electric and magnetic field to enter, right? Electric field is zero inside a metal, so electromagnetic wave cannot go in, but we are approximating electromagnetic wave in a ray in straight line. So that's your incident ray. We use an abstract line which is perpendicular to the mirror. So we can state this is a mirror. A mirror technically is a metal. Any perfect metal acts like a mirror. Better the property, better the metallic property of the surface, better a mirror it is. If it is a perfect metal, then you would say it is 100% reflecting mirror. If it is not perfect, if it is slightly insulating, then it will not reflect all of light. Instead, it will reflect about 80 to 90%. Most of the mirrors that we use have a reflection property of more than about 98 to 99%. So they're reasonably very good to within 1% accuracy to be a perfect mirror. That's your incident ray, and the law of reflection says that the angle of incidence, the angle it forms between the incident ray and the normal ray, is exactly the same as the angle it forms after reflection. So that's your theta phi. So this is let me call it theta r. That's reflected ray, and that's incident. This is normal. Sometimes you say it's a ray, but it's a normal line. It's an abstract line. No physical quantity is actually going. It can go incident ray, could be having a zero angle. In that case, it goes along the normal line, and then the reflected ray is exactly the same. So law of reflection is the simple statement that the angle of incidence is exactly equal to angle of reflection. It's almost like if you were to throw a ball, if you throw an elastic ball on a wall, it typically reflects such that the angle of incidence is exactly equal to angle of reflection. So that's all there is in law of reflection, and then you could add a statement that all this is happening in a plane. When we are drawing it on the surface, it is you don't realize that actually when you simply say the angle of incidence is angle of reflection, there's an ambiguity there that this could be coming out of the plane, and still you could have that angles to be the same. So there is an added restriction that all three rays, the reflected ray, incident ray, and the normal line has to be in a plane. So that's law of reflection, and we would like to analyze this for spherical mirrors. So we would like to have this interface not really a flat surface. We would like it to be spherical in shape, and we would like to investigate what happens. So spherical mirrors. So there are two mirrors we talked about. One is concave mirror, and we introduced a line, and I was not recollecting what's the name of the line. It's called the optical axis. That's the definition of optical axis. So it's again an oriented line. So the direction in which the light is going is called the optical axis. And if the cave side of the spherical surface we are talking about, that's your surface, and is painted on one side. By painting, I mean it is coated with a metallic paint, so that you save on the, like, metal is more expensive than glass, so you save on that. So you simply want a thin layer, and glass is just acting as a substrate there. The optical axis is facing or falling onto the cave side of the surface. Cave, so that's why it's called a concave mirror. And that is a radius of curvature. The center, this is radius of curvature. That plays an important role in our analysis, that the property, the whole mirror now is described by one parameter, and that's what's the radius of the sphere it is taken out of. That is also what is called convex mirror. There are two types of mirror, and again, that's your optical axis. And this time you have the surface configured in such a way, and the metal is painted on to the cave side so that the light comes on the convex side. So this is convex in shape, so it is radius of curvature would be negative in that sense. So the light comes and hits on the outer surface. So when it is reflecting, so then one point that will come in is that when light is coming in, it reflects in such a way that it is converging. So it's also called converging mirror. And here, when light comes in, it tries to go away from the axis, so that's called a divergent lens. We will illustrate this more as we go down. That's okay. So now we have two mirrors. In fact, there are three mirrors, right? There is concave, convex, and somewhere right at the border it is transforming from concave to convex, and that's a flat mirror. So this is this has a positive radius of curvature. This has a negative radius of curvature. Exactly infinite radius of curvature, or I should say, radius of curvature is infinity, but what's the word? 1 over radius. What is it called? 1 over the radius of curvature. What? Okay, 1 over radius of curvature is a property independent. So when it is infinite, it becomes 0. So that is a word associated with it, but not important. It is not it's a mathematical expression. You might have seen that somewhere. So there are three types of mirrors. Concave mirrors, or at least in this context that we're talking about, when we talk about spherical mirrors, there is concave, convex, and flat mirror is also part of that, in the sense that it has infinite radius of curvature. We would like to have an equation that governs this equation or for this configurations, and let's try to derive that. So that's the optical axis, and that's my spherical surface, and we have the mirror itself being part of that, and we will derive this. For we are pretending that this is concave, but we want to keep only a direction, but the particular axis that passes through the center of the mirror, or the center of curvature, serves as a reference line. And if this is my object, so this is my object. Object means light originates from there, and let's say light goes and hits that. I'm following one particular ray. When you have a source, rays are going in all directions. And what we discussed in the last lecture is that if I were to follow two rays and construct a cone out of it, and extrapolation of those two lines will give me where the image is formed. So that's one of the rays. And when it is falling on this surface, that's my angle of incidence. That tiny angle is the angle of incidence, let me call that angle theta. Law of reflection says that the reflected ray at that point will be such that it has to make the same angle theta and it has to be on that same plane. So it will come in this form. In such a way that this angle is exactly the same as that angle. So that's the same angle theta. The theta initial is the same as theta reflected. So that's what the system will try to do. The ray of light that is coming in there, the reflected ray has to be the same. And from that point on, so that's our concept of the geometry if you want. What else can we conclude? Let's put in some angles. Let's say this is alpha. That's your object. Let me call this image. It will turn out to be that that's my image that is formed. And we'll see that more elaborately very soon. Let me call this beta. And here, that's gamma. So let me zoom that in. So I have beta, gamma, alpha, that's theta, that's here. Whenever you have a triangle, the two inside angles will be equal. The sum of the two inside angles will be equal to the third angle, but it is an outer angle, right? This will be the angle inside the triangle. Gamma will be equal to alpha plus theta. So we can immediately conclude that alpha plus theta will be equal to gamma. And the same thing for this triangle here, that gamma plus theta will be equal to beta. I want to be talking in terms of object and image instead of the reflected angle, because this point, there are many points there. It is in reference to object and image. I want to do my analysis, so I want to get rid of this angle theta. So this is there in both equations. If you were to take alpha on the other side and theta on the other side, I get this equation that gamma minus alpha is equal to beta minus gamma. And which can be written as take the alpha on the right, bring the gamma to the left, and then revert it again. So this is the same as alpha plus beta is equal to 2 times gamma. Simple relation, just came out of geometry. So this was a mirror, spherical mirror. I kept a point which I'll interpret as my object, reflects off the point, reaches here, that will be interpreted as the image. And there is a simple relation between these parameters, that alpha plus beta will always be equal to twice the angle gamma that the center that the normal line makes. But I would like to talk in terms of distances instead of angle. So let's define the object distance to be the distance from the object to the mirror, and that will be my object distance. So that's object distance. And this will be my image distance. I, that's my image distance. And this we already said is the radius of curvature. If you look at it here, the triangles it is making is this is image distance di. That's my radius of curvature, and that's the object. It's like saying there are three triangles. This is the same vertical line, but it is serving as a side for this triangle, that triangle, and the third triangle, which means that tangent of alpha will be the height over the O, tangent of gamma will be height over R, tangent of the or tangent of beta will be the third distance. So let me write that down. So you have tangent of alpha is equal to height h over object distance. Tangent of beta is height h over the image distance, and tangent of gamma is the height h over the radius of curvature. Because the vertical part of the triangle is common to all three. That is one approximation we are going to use in this whole analysis. That's for simplicity, and it is necessary. Is that we are going to talk about a small patch on that mirror, which is right around that optical axis. So we do not want the mirror to be very large. That's why we do not talk about a whole dome. So it's a very small patch you're talking about. And in that small patch, alpha will be small, beta will be small, and gamma will be small. So if all three angles are small, so that is alpha small compared to what? Alpha is an angle, so it is radians. So it is compared to 1 radian. That's 1 radian. Beta is small compared to 1 again, that is radian. And gamma is small compared to 1 radian. Under these approximations, that is a nice feature. If you take a calculator and do sine of work in radians, and you do sine of an angle, and then you do the same thing with the angle itself, it will come out to be the same. Sine of an angle is pretty much the angle itself if you're working in radians. So we will approximate this to be alpha. We won't work with tangent alpha. We'll just say this is beta, that's gamma. This is very accurate if you're working within 10 degrees. It doesn't have to be small. By small, we mean like remember 1 radian is about 60 degrees. So 57 to be more precise, to 2 significant digits, to 1 significant digit is 60 degrees. So as far as you're small compared to 60 degrees, so for example, 6 degrees is small. It is accurate to more than 1%. And in that approximation, it is sufficient to work with this ratio instead of this tangent, or work with this angle instead of the tangent of alpha. And that leads to a lot of immediate simplicity if you want. So we have alpha plus beta is equal to 2 times gamma. If you substitute this in, what we learn is that there is h there, but they get cancelled. You learn 1 over the object distance plus 1 over the image distance is equal to 2 over the radius of curvature. And that's going to be your mirror formula. That will be your central formula which you will analyze for all spherical mirrors. This was the derivation. You need to have the information. There are these concepts that goes into it, that for example, tangent alpha is alpha. Basically, you're doing this for small angles. This equation is not applicable if you were to take a very huge mirror. So in that case, you have to be more accurate and use the full trigonometric equation. And so those are the concepts, but most of the time we are it is sufficient to use this equation. Since this factor of 2 shows up here, that's every time you have to divide that by 2. In fact, you call this a new Diameter, you say this is 1 over f, where f is r over 2. So half of radius of curvature. Remember, radius is itself half of diameter, and half of the radius is what is called the focal length of a spherical mirror, and that's what shows up in the equation. What the inverse of the object length plus the inverse of the image distance is equal to the inverse of the focal length, and we will see how we will use this point. Let's introduce some sign conventions. Most of the time, it is convenient to do things from the scratch, and then you don't need any of this sign convention. You just use law of reflection, and that's sufficient. But often, especially if you were to do compound mirrors, you are doing this multiple times, then you want to get more efficient, and then you create some conventions associated with this configuration. So we will have, that's your optical axis that serves as a reference. That's your optical axis. And somewhere you keep the mirror. So I'm just keeping this as a straight line. Remember, even though the mirror is curved, you should always imagine that to be relatively flat, because we have used an approximation that it is small angle approximation that requires that the mirror is significantly flat in that small region we are talking about. So this is a spherical mirror. And it could be concave or convex. Either way, if it is concave, it will be bent like this. If it is convex, it will be bent like this. So it is good to draw them, but whenever you're doing the geometry, go all the way. We don't end at that curve surface. We have 3 parameters in those equations. Let's begin with the focal length or the radius of curvature. So the focal length, which is half the radius of curvature. The radius of curvature will be positive on the left, and it will be negative on the right. That means to say that if it was a concave mirror, it will look like this. Its radius of curvature is here, so it is positive. And so that's a concave mirror. If it is a convex mirror, it will look like this. And its radius of curvature is somewhere here, and that will be a convex. Often concave mirrors are called converging mirrors, and convex mirrors are called diverging. Examples help. A concave mirror is what you would use when you are trying to look into a vanity mirror or a shading mirror. So whenever you look at a fine thing, you're trying to look at a face and you want it in a magnified form, that's a concave mirror. A convex mirror, a classic example is the rear view mirror, right, of a car. The rear view mirror of a car is a convex mirror. So that's the reference you can keep. So this is a rear view mirror in a car. A car is reasonably common in today's life, so that's a good example. And here, this is what should I call it? A shading mirror, a vanity mirror. I think, what do you call it? Mirror.
Mirror over the sink.
Mirror. Tell me.
Like you go to like a hotel, they have like it on the wall.
Yeah. What do you call them? What's the word? What should I write there? Vanity, reasonable? Yeah, it's not a bad word, right? No, it's not a good word.
Like a hand mirror. Like a hand mirror?
Yeah, hand mirror. Yeah, okay, let me call it hand mirror. Maybe vanity is too strong. Hand mirror. That may not be conveying the point. Okay. Okay, so I think we understand what it is. It helps to have a visual feel for what we are talking about whenever we are doing this. Okay. Object distance. Again, will be positive to the left, negative to the right. This will be called a real object. When you keep an object in front of the mirror, then you say it's a real object. You say, how can you stand behind the mirror? That's impossible because then light doesn't follow you at all, so you're in the dark. But if you're doing compound mirrors, you can actually create an image that is behind the second mirror, and that serves as an object for the second mirror. We will not be discussing that, so we will not have that opportunity to discuss a virtual object. But you can at least try to imagine that, yeah, if you have compound mirrors, that is a possibility. Image distance, again, will be positive to the left and negative to the right, and this will be called a real image. And this will be called a virtual image. In the usual bathroom mirrors that you are seeing yourself, you see an image. Where is that image? That's behind the mirror. So that's behind. So is the mirror that you see of yourself when you're standing in front of a bathroom mirror, is it a real image or is it a virtual image? Real versus virtual. Right? It's a virtual because it is behind the mirror. Right? That's an immediate conclusion you can make, but we'll see the analytic part very. So that's your definitions if you want, and you need to get a better feel for what virtual image is, real image is, and diverging and converging in the examples that we will do. We'll introduce one more notation that an object, sometimes you will see that in mirrors, they're also inverted. Like if you have some kind of mirrors, you can get invert yourself. So we need to have vertical and vertical reference also. So let's say that's going to be positive and that's going to be negative. Right? Let's say that's positive. So this will be inverted if the image is upside down, that's inverted, and what's the opposite of inverted? Upright? Is that correct? Inverted, opposite, okay. So that's going to be another reference. Let's do an example to clarify these things. For example, so and of the few examples that I'm going to do, I mentioned earlier that there will be two questions in the exam which will have exactly the same format. I ask that every year. This is one of these examples. There are multiple examples you can build where you keep the object, but there is a limited number of them, probably 5 to 10 examples you can construct for each mirror. And I always ask one out of them. So the question will be, let's say you first decide on a mirror, let's say it's concave mirror of Sometimes you will say a converging mirror. Converging means it's a concave mirror. Concave mirror of focal length of 10 centimeter focal length, let's say. So 10 centimeter focal length. Notice I did not tell you whether it is positive or negative. Since I have given you concave mirror, focal length means it is positive 10, right? So the information given is x is equal to 10. I'll write that in a minute. An object is placed 30 centimeter in front of the mirror. Right, so that's a new information. Object is placed. So we are talking about an object distance. It is always object distance is measured from the mirror. And the question is, where is the image formed? And what are its properties? By its, I mean the properties of the image. And in the exam or whenever I'm asking it, I specifically ask each property, but it's easier to just write what are its properties. How do you go and analyze this? So we'll use this equation very soon. As I said before, try to use a ruler. You will notice that even though I'll try to be careful, even then a small deviation in the angle leads to a very large deviation when you extrapolate it to a far distance. First, we draw an optical axis. That's your optical axis. That's the direction in which light is going. And you have a reference line which serves as your mirror. It's a concave mirror. It is good to draw the fact that this is a concave mirror, but this is just a mnemonic, if you want, a cartoon. It has to have a small or a large radius of curvature in the sense that it has to be very flat. We approximated the angle to be small. So this is just to convey to me that this is concave, but when I bring in my rings, I cannot use this as my point. This line is what is more important. For all practical purposes, I bring in my lines all the way to the straight line, and that curve, a curved mirror I have shown is just for a visual clarity that that's a concave mirror we are talking about. That is the focal length, so it's given that focal length is equal to plus, right? It's plus because it is a concave mirror. And the object distance, it is kept in front of the mirror. Again, it is plus, and it is plus 30 centimeters. Whenever we want to have a ruler, we want to have these divisions and the scale, if you want, associated with the optical axis, and the scale is completely decided by the focal length. So focal length is to the left, so that's my reference, that's my x. Let's say this is 2 times x. That's 3 times x. And so on. That's 10 centimeters, that's 20 centimeters, that's 30 centimeters. If this was 30 centimeters, that's 30, 60, 90. So once I have the focal length, I can scale the straight line. So that's my focal length to the left. So that's 1, 2. In principle, this is plus 10, minus 10, minus 20, and so on. Right? That gives me a reference in a sense. Where is my object placed? It is placed 30 at 30 centimeters. That's here. And earlier, when I was deriving the equation for the mirror, I used a point, but now we want to clarify that This is an object we are placing it as a vertical height, so you could be standing in front of the mirror. That will be represented by an arrow. So that's your head, that's your tail, so that's a human standing in principle. If you want to imagine it like that, but an arrow serves the purpose very well. The height of this object will be called h0. And this distance is d0. So let me just write it here. That's the d0. And the distance from the center of the mirror to the object is my object distance. Focal length is decided by what's the radius of the mirror, and that is the height of the object. And I need to give you that. So let's say an object of height, let's say height is, let's call it 1 centimeter. 1 centimeter object. If it's a human standing, then they are much taller, but let's keep this small. Okay, how do we go about finding the image? There are two ways. One is going to be algebraic. We use the equation that we derived, but more important is a ray diagram. Using just geometry, we can decipher where the image is going to be. Remember, we have to follow two rays, and wherever they intersect, our eyes will extrapolate or project it backwards, and it will interpret an image point or image that is formed. So we need to trace two rays. First, we go all the way straight, parallel to the optical axis, and when it hits the mirror, so it is, if you go by this cartoon that I've drawn, it has to hit here. But remember, that was a cartoon, it is actually reasonably flat that you will not be able to tell the difference. So you have to go all the way in there for whenever you're drawing. For drawing purposes, go all the way to that straight line. Now the question is, where does this go afterwards? Because I do not have my geometry anymore helpful, because I have not drawn this sphere correctly. So how do I know where this will go? So now we use our equation. Remember, 1 over object distance plus 1 over image distance is equal to 1 over focal length. And that equation is valid both for concave mirrors and convex mirrors. So how does that help? When I say this is a ray, that is, so this is ray 1, let's say. The ray 1 is coming parallel to the optical axis. That means to say that it doesn't have to be coming from this particular point on the object. It could have been coming all the way from the back side, and still I won't be able to differentiate. All the lines are parallel, and parallel lines by definition start from infinity. So object distance could be infinity. So if I were to write that, so 1 over infinity plus 1 over image distance is equal to 1 over focal length. That's approaching infinity if you want. A very large number here. 1 over a very large number is practically 0. That means that implies that this is equal to this. So the image distance is exactly the focal point. So that's the importance of the focal point. If the image, if the object was very far away, the image is formed at the focal point. So that's the concept. If you want, take a mirror, and for us, infinity is whenever it is large compared to the focal length. If you have a 10 centimeter of a mirror of focal length 10 centimeters, 1000 centimeters is to 2 significant digits, infinity. 1000 centimeters is 10 meters. So if you have a small mirror in your hand, which has a radius of about 10 centimeter, and you're 10 meters away, which is within this room probably, that's practically infinity. That's why you will often see people who are working with mirrors, they try to focus a point which is far away. By far away, mean a tree, and wherever the image is formed, that's your focal length. So you don't have to do too much work. Just focus a very far object, wherever the image is formed, that's your focal length. So The point is object distance infinity means the image is formed at the focal point. When you come parallel, you're coming from infinity, so this ray has to go through the focal point. So that's the first rule. Draw a straight line parallel to the optical axis. After reflection, it has to go through the focal point. So that's rule number one if you want when you're trying to draw the ray diagram. So that's your ray one reflected. The second ray, make it pass through the center. That means it is the normal line. Right? That's your normal line. Wherever it goes in it's the normal line. So that's your, in principle, if this is a toy model, that's your surface, it will reflect back. And it will, wherever it goes in it's a mirror, it will come back. So it goes and it comes back. And when it comes back, it goes this way. That's ray 2. Remember, our eyes interpret two rays as make it extrapolate going backward. Wherever they meet, that's your image. Where does ray 1 and ray 2 meet? That's this point, that's your head. And that's your image. Make a line vertically towards the optical axis. That's your image. So that's the eye. This is optical axis. So the point is, if you were to stand in front of a mirror, the image is inverted. Will you see this image? Yes. If you were to have an eye here, that's your eye, and you can come closer so that the cone goes into this. So that's your eye. And these two rays going back into the eye, we project it backward, and that's the image form. You can almost read it out where the image is. This was 10 centimeters, that's 20 centimeters. It seems like the image is formed at 15 centimeters in the front, and it's a real image according to the sign convention that we have. What do we mean by a real image and a virtual image? A simple intuitive or by examples, if I were to illustrate it, the image that is formed in your bathroom mirror, that's a virtual image. What is the example of a real image? Often we use the PowerPoint projector. That is an image formed on that PowerPoint, on that screen. That's a real image. That's real image in the sense that if I were to keep my hand there, my hand will get warm. There is energy at that point. Whenever, if I were to keep my hand at this point, I'll feel the heat because light is converging there. There's a lot of light coming in there. I'll feel the heat. It might be very small, it may not burn me, but still I'll feel the heat. On the other hand, in the bathroom mirror, I cannot even go and keep my hand there because it's an abstract point. It is inside, and that's why you call it virtual. You cannot even take your hand in there, so there is no point of talking about whether it will get heated up or not. Can we do this analysis analytically? Yes, but let's very quickly talk about what are the properties. It's an inverted image. So what are the properties of this image? It is inverted. It is real because it is on the left. It's a real image. Inverted image. And we are also interested in whether this image is magnified or diminished. Sometimes it is smaller, sometimes it is bigger in reference. Of course, it could be very rarely exactly the same height. So in this case, it seems like it is smaller or what is called diminished. Small. That's your three properties, but now we want to quantify it. When you say invert or when you say smaller, by how much? Like if that is 1 centimeter is the object, what exactly is the size of the image? For that, we have to go and use our equation. So now let's use those equation, we have 1 over object distance plus 1 over image distance is equal to 1 over focal length, 1 over 30 centimeters. Let's keep it in centimeters, everything is happening in centimeters and only distances are involved. Image distance is equal to 1 over 10 centimeters. Move it to the right. That's 1 over 10 minus 1 over 30 multiplied by 3 plus 3 minus 1, so that's 2 over 30, and that's 1 over 15. But that's inverted form, so image distance is 15 centimeters, which is very clear in this image. This is 10 centimeters, that's 20 centimeters, that's pretty much close to in the center. So it is indeed 15 centimeters. How do we know that it is a real image? This is plus, right? So that's equal to plus 15 centimeters, right? It comes out plus. The plus sign tells you that it's a real. We also need to talk about whether it is inverted or not. If it is inverted, how much is it? That is a formula for magnification. So magnification formula. The two equations basically. This is the one slightly extension of that. One is this is the mirror formula, and then there is the magnification will be defined as the height of the image over height of the object. Right? If the height of the image is larger than the height of the object, it is greater than 1, otherwise it is less than 1. But it is also sign dependent. If it is minus, that means it is inverted. This is also equal to the negative, what is the negative sign? Image distance over the object distance. Okay, that's a convenient formula you have. So now that we have the image and object distance, we know how the magnification would be. So m would be equal to minus of image distance is 15 centimeters divided by 10 centimeters. That's equal. No, what's the mistake? But it's smaller. That's not 10, that's 36. That's 30. Units cancel out, that's 1 by 2, so that's minus 0.5. Right, to two significant digits, it's 0.5. The negative sign here tells you that it's inverted. And the fact that this is less than 1 tells you that this is smaller. If it is greater than 1, it is bigger. Positive means it's upright, negative means it is inverted. Right? That's the analysis that goes through. There are how many cases possible? You can have this object distance farther than B0. You can have somewhere in between. You can have exactly at this point. You can have exactly at 2 points. Then somewhere in between here. It can be somewhere here, or it can be somewhere here. Is it always a real image? Not necessarily. So let me very quickly give you an example where the image form is not really for the same concave mirror. Let's another example, concave again. Let's say concave, and f is equal to plus 10 centimeters, and let me say the object distance is plus 5 centimeters. So you're getting very close to the concave mirror. That's what happens. Notice I image form is inverted. But that's not very useful if you're using it as a hand mirror. You see yourself inverted. That's not what happens. Right? You really see yourself upright. So what's wrong here? If you use that mirror, if you had to move the mirror farther, you may, in fact, you won't see anything inside that at all. It's complete. It seems that's my image, and inside the focal distance. Again, draw the parallel. My rule is first go parallel, and after reflection, any line that is going parallel goes through the focal point. That's my focal point. So that's ray 1. The second ray has to go through the center of curvature, and it goes undeviated. It goes and hits the mirror and then comes back. Okay, so the second, that you start from the head, go through this point here. So that's here 2 times. And the idea is that this somewhere goes and completes it, goes and hits that mirror and comes back. Or you can imagine that this goes this way. That's a cone formed already, you can see. And if you were to have an eye here, we will project these 2 lines backward. Wherever it meets, that's going to be our image. And you will notice that this is somewhere here, at the back. That's your image that you see inside a hand mirror, or that's what you want to exploit. There are 2 mirrors that can be formed. One is an inverted when you're very far away. When you're very close away, it is magnified. That's what you want to exploit. So you bring the mirror. We learn this based on our skills that we learn in life, that you bring the mirror very close, and there is a magnified mirror you form. You exploit that, you can see yourself more closely. So that's a magnified image. And this distance, it seems like if this is the focal length, that's very close. If this was plus 10 centimeters, it seems like it is a negative 10 centimeters. Exactly, we have to do that analysis. But I will leave that separate for you guys to exploit. But I will here do the example of a convex mirror example in the last 10 minutes. Any questions at this stage? Okay. Maybe I should write this down here. This is a virtual image. Virtual image. Because it is formed on the right side, it is magnified. And it is upright. This should be contrasted with the image that you see in your rear view mirror. There also it's a virtual image because we are usually more accustomed to seeing virtual images. It is not magnified, it is upright. It is convenient to see upright, otherwise we have to use our brains to interpret that. But they're smaller. In fact, you will read on the mirror next time you see the rear view mirror in small print. They write that images are farther than they appear in the mirror. And that's to take care of the fact that it is not magnified, it is actually diminished. It is smaller, so that more things can fit into that. Again, it serves a good purpose, but there is a illusion also associated with it. So let's see how we can see through those examples. Example. And this time, let's say this is convex mirror, which is also a diverging mirror. And the moment I say focal length, a convex mirror, this means that it is minus. And let's say it's 10 centimeters. Let's keep everything uniform. It's taken to be 10 centimeters, but you can have many. Many for that. When you're using a rear view mirror, because the cars are typically far, right? So it's not within a small distance. You cannot expect that, oh, let the car come very close to the mirror, only then it will give you an upright image, but it's supposed to work for very large distances. So let's say the object distance is just so that we get it right. Let's keep it not too far. Let's say again 30 centimeters, right? Earlier we did for 30 centimeters. And where is the image? What are the properties? That's a question you're asking. That's your optical axis. That's your reference line where you want to keep the mirror. This time, the mirror is this way. That's your convex mirror. Again, this is just for reference. The curvature is not to scale, so you don't want to use that curvature while you're drawing. Where is the focal length? It's minus 10 centimeters. It's to the right, not to the left. It is to the right. Unlike the other two examples that we did, that's your focal length. That's my 2 times the focal length, and so on. And on the left, I will just have a reference point, and that's why this is plus 10 centimeters, minus 10 centimeters, plus 20 centimeters, minus 20 centimeters. To make sure the line there is clear, and this is optical axis. Remember the sign convention. In fact, in mirrors it is convenient. Everything is positive to the front side of the mirror if you want. And the lens, when we are doing, we'll mix it up, it will be a little more confusing. But here it is convenient that everything is positive to the left when I'm facing the board, and or in the opposite direction of the optical axis, if you want. 30 centimeters is back where I keep my object. It is positive. That's focal length, that's the third point here. So that's my object here. And again, use the same rule. Ray 1 goes parallel. Remember, I don't go all the way till here because that's just for my visual reference. That's my ray 1. Anything that comes from infinity goes through the focal point, so it has to go through this point. But light cannot enter the mirror. Light cannot enter it, so it reflects off it. So it's supposed to reflect back, but it doesn't really go through the point, but it seems like it is coming out of that point. So it is reflected off from the focal point. Notice the difference. A parallel line came here, it goes into the focal point, converges. That's the converging part of the concave mirror. Light cannot enter the mirror, so it is actually reflecting off. So that's the diverging part of the mirror. So it's going away from the optical axis. Here it is going towards the optical axis. That's ray 1 if you want. So that's ray 1. Where is ray 2? I have to go through the center of curvature. And where is the center of curvature? It's all the way here. Don't confuse with this. It is not 2 times on the left. It is with reference to the focal length. It is 2 times the focal length. So I have to go to this point. I draw a straight line there, but I cannot enter the mirror. So I cannot enter the mirror. My ray will come back and it will go this way. So that's ray 2. And my eye, which is somewhere here. Yeah. That's my eye. And wherever these two, that's not really straight line. Wherever these two rays meet, that's where my image is formed. It's very clear it is here. That's my image. Smaller rear view mirror, notice images are smaller. It is good. You can compact a lot of information in a small area. That's your image. It is virtual. It is to the right. It is negative. So it is virtual. It is smaller and it is upright. In fact, usually the cars are not 30 centimeters away. They are 3 meters away or maybe 30 meters away. And as you go farther and farther, this point will get closer and closer to the focal point. For all our purposes, the images of all the cars are formed on the focal point of the mirror. So it is right on the focal point itself. How much deep it is, that's the curvature of the mirror decides that. We can, only 1 minute, so we can actually do the analytic part also and get the same things in there. In your homework, you see more explicitly for each example that is worked out. And remember that there is a solution also available if you use the same idea. So refer to that. One of these examples in some form will surely appear in your exam. So it's a useful thing to know and just to learn also. Thank you. It is